Hey, this is Charlie Thompson, and welcome to the video for Lab 15 on rivers. So this lab video is going to be shorter than a lot of the other lab videos. There's not a whole lot to go over that is special for this lab. A lot of what we're doing are skills that you've already learned. So really, there's not a whole lot of new material for you to be learning this week. So what are we going to cover? You're going to be finding horizontal distance using maps and Google Earth. You've already done that. You're going to find relief, and you've already done that using maps and Google Earth. You're going to find the slope in feet per mile. You've already done that. You're going to find the sinuosity, which is just a fancy word for how wiggly or curvy a river is. You're going to identify some floodplain landscape features. You're going to identify drainage patterns. I'll explain that in just a minute. And one of the keys to identifying drainage patterns is just knowing where the location is of the drainage pattern that you're looking at. I think I've mentioned this before, that I think a lot of the geography that we do is like artificially hard. If you know the area that you're looking at, you, as a geographer, you'd have an idea what the forces are, the tectonic forces, the endogenic, exogenic forces that have shaped that place. And then you'd also have a really good idea starting out what the drainage pattern would be. All right, so this lab you'll be using Google Earth. There's no KMZ file to download. Everything is just in the link. You click the link and you'll open up the Google Earth project. And again, almost everything you're doing, you haven't had to find sinuosity. You haven't had to identify floodplain landscape features. And I've included a video, my lecture video. If your teacher hasn't gone over rivers yet, you would really benefit from watching my lecture video on, for example, the drainage patterns and the floodplain features, because you're going to have to identify those. In my lecture video, I go over in more detail what they look like and all that stuff. So if you haven't had rivers yet in your lecture class, I really highly, strongly recommend that you watch at least those parts of my lecture video that cover, for example, floodplain features, drainage patterns, some of the other aspects of rivers. So, for example, scale, you're going to have to find the scale of some maps really quickly. All you got to do is put both sides into the same units. So if it's, inches to feet, you put both into inches or put both into feet. It doesn't matter as long as the left and the right are the same units, and then divide both sides by the left-hand side so that you can get it into the format of 1 to whatever. You're going to be finding a representative fraction, or RF scale. So put both sides into the same units. Do what you need to do. Use unitconverter.com. I would recommend that. And then divide both sides by the left-hand side so that your fraction is expressed in the format of 1 on the left to whatever on the right. How to find slope as feet per mile. We've already gone over how to find relief and horizontal distance. So once you know the relief and the horizontal distance, you just divide the relief by the horizontal distance and multiply it by the number of feet in a mile, 5,280, and that'll give you the slope expressed in feet per mile. So sinuosity, you haven't had to do before. Sinuosity is a measurement of how curvy a river is. And there's terms that apply to the different shapes of rivers depending on how sinuous they are. Straight, a straight line would have a sinuosity of 1. So straight from 1 to 1.05, if the sinuosity is between 1 and 1.05, it's straight. 1.05 to 1.25, we're going to call that sinuous. 1.25 to 2, meandering. And over 2, so what that would mean for a highly meandering stream is this distance is in blue of the river miles would be twice the distance, or over twice the distance of the straight line distance. So it's super simple math. You just divide the river distance by the straight line distance, and then look at the chart to see what the descriptive word is, the term for that river shape. So, for example, we've got this river, we measured it's 2 miles long. The straight line distance for this going from the start point to the end point is 1 mile. 2 divided by 1 is 2. Sinuosity is 2. That's pretty much it. This is a map of the Fiske expedition. Fiske was a geologist who was looking at the former channels of the Mississippi River. I think this is out by Memphis. And you can see there's, in white is the current, and then older and older and older and older channels on the Mississippi. And he did this for the entire length of the Mississippi. And this figure, if you were to print it out full size, would be about 3 feet by 4 feet. And they're just gorgeous. They're absolutely beautiful. But you can see, like, here's an oxbow lake. These would be meander scars. I'm just including it. It's the image you see when you start the chapter. And I thought I would explain a little bit what the hell you're looking at. Really an amazing, beautiful, beautiful, beautiful scientific work, and also a work of art. Okay, meandering. So the physics of rivers, and I've put a couple videos on the meandering process, but the physics of rivers is such that as a river flows downhill, they almost never flow in a straight line. They curve. And as a result of that shape, of the curving shape of the river, the fastest water and the ability of a river to transport or erode depends on the speed. The speed, to some extent, depends on the slope, how steep it is. Steeper rivers travel faster. It's pretty easy to make sense of. But within the river, on the outside bank, the river is actually, that's where it's going fastest. So it's picking up and eroding on the outside bank. The inside bank is where it's going slowest. And so new material that's being transported, the alluvium that's being transported, gets deposited at the inside bank, making what's called a point bar. So we have deposition in the point bar, and then we have erosion on the outside cut bank. And this process continues. The curves get bigger and bigger and bigger until they actually cut through, and then the river straightens out and flows faster, which means that it curves even faster. But right now, I want to go over the key terms of the cut bank, which is the outside bank, and then the point bar, which is the inside. There's point bar, deposition at point bar, erosion at the cut bank, the outside bank. So, Wooded Riverbank Twilight by the artist Isaac Levitan. Clearly, this is the cut bank, and here is the point bar. So the river would be traveling fastest around this outside edge and removing material. And at the same time, the same stretch of river on the inside bank is where it's traveling slowest, so that's where material is being deposited. And here we've got a time-lapse of the Ucayali River in Brazil from 1985 to 2013. So you can see there's point bars. The gray material is the material being deposited. There's a cutoff, and now the river flows through there. It's going to abandon this. This is going to become an oxbow lake when it's cut off. And then over time, it'll fill in with vegetation and become what's called a meander scar. So I would watch this. It's in the slides. It's in the video. I'd watch it a couple times just to see how the river changes from 1985, where you can see here's the cut bank, and the cut banks actually flow towards each other. They grow rather towards each other. The river width doesn't change because there's deposition on the inside bank as there's cutting on the outside bank. They flow together. Now the river's ripping through here. This channel gets abandoned. It's going to silt up at the where the water was flowing in and out. It's going to silt up and get cut off and become an oxbow lake. And then over time, like I said, it'll fill in with organic material and become what's called a meander scar. I've included this video. It's an excellent video. I love it, except, and I'm just going to fast forward to the part that drives me crazy every single time. So they start with a straight river, and then they have this stupid muskrat thing. So you can't find a straight river. Rivers aren't straight. If it's straight, it's because it's a human-made channel. But rivers, they never start straight, so they do a really good job of explaining that there's higher velocity and erosion and lower velocity and deposition. But please just ignore the whole bit about muskrats if you watch the video. Just remember, all rivers start off wiggly, and they just get wigglier. So meandering, again, this is a a non-animated version. We've got a point bar. We've got a point bar. That would be the cut bank on the outside, cut bank. And then because this is where the river travels fastest at the outside, at the outside bank is the cut bank. It says undercut, and usually called cut bank. The cut banks are going to flow towards each other. And then when you get a cutoff, that's going to be the new high-speed channel for the river. And the river's traveling quickly here, and it stops flowing through here. And this will silt up, that will silt up. And then you end up with an oxbow lake. Over time, as plants grow and die, it'll get filled in and become a dry meander scar. So here we've got an example of a river someplace in the mountains. You can see point bar, you can see point bar, you can see point bar, and then cut bank. Like there's no trees. You can see the trees, it's just sand and then grass and then baby trees and mature trees. As this material gets deposited and it moves inward, this material is going to get eroded. So these trees are going to get killed. They're going to get washed away until it cuts through. You'll get the cutoff, and then that'll be the new channel, the new main channel. So here's an example of the Mississippi River, and I wanted to go over the physics of what happens. And if you were going, so this is the river miles going from point A to point B. It used to take 48 kilometers to go from A to B. In 1722, the river cut off. There was an oxbow lake. But now going from A to B only takes 9 miles. So the river is much, much, much steeper, so it's going to flow faster. And so you'll get faster erosion after the cutoff. As the meander bends grow and grow and grow, the slope gets shallower, so the river flows more slowly, so it erodes more slowly. And then it cuts off, and then it's steep and fast, and it'll erode very, very quickly, so you get really rapid. And then as the slope gets shallower, it'll get slower. So it goes back and forth. There's a cutoff, and it erodes quickly, and the bends get bigger and bigger and bigger, and the river's traveling more slowly, and then it cuts off. And there's a map of the Mississippi River with the False River. We will be looking at this part in the lab exercise that you'll be doing. Some floodplain features, very, very, very important. We've got Oxbow Lake. We've got a meander scar where the river used to flow. This would be another Oxbow Lake. A Yazoo stream or Yazoo tributary. One of the things that rivers do is every time they flood, they deposit sediment at the banks. And the banks get higher, forming natural levees. So every time the river floods, the banks get a little higher. So if you had a tributary, which is a stream that wants to join the river, the tributaries in some places can get blocked by the levees. Like water doesn't flow uphill, so it can't flow into the river, and it just flows parallel until there's a break in the levees, and then it flows in. So a Yazoo stream or Yazoo tributary is a tributary of the river that can't initially flow into the river because of the levees blocking it. So a Yazoo stream tributary flows along and then eventually flows into the river. Back swamp, it's just an area where it would be swampy. The levees are higher, these banks are higher, so you could actually have a slightly lower area in here where water would accumulate. And I think those are all the floodplain terms that you need to know. You've got point bar, you've got cut bank, undercut, cut bank, point bar, oxbow lake, meander scar, Yazoo tributary. Okay, drainage patterns refer to the overall shape of a river. And drainage patterns are fascinating. They're a result of how steep the river is. They are a result of the geology that's underneath the river. They are a result of how much water is flowing down the river. They are the result of geologic processes in the past. For example, in deranged drainage areas where they were continentally glaciated. So these are dendritic. They look like trees. They are the most common. It looks like these are a little bit more parallel than these. These are dendritic, very clearly dendritic because they look like trees. The most common drainage pattern. So I was just messing around on the East Coast, looking at drainage patterns, and I realized a lot of dendritic. And then in here, you've got some trellis drainage in this belt. if I turn on just the shaded relief, oh yeah, that's what I was trying to look at with this, is just looking at the rivers. So looking at just the rivers as a geographer, eventually you'll get a really good sense of what the landscape looks like. For example, you can see the rivers in here are lines, and here they look more like trees. They're crooked and curved. And so that tells you as a geographer something different's going on in here. And if we look at the shaded relief, you can see, oh yeah, clearly there's this big band of folded mountain ranges, the Appalachians. And here there really aren't, and here there aren't. So if we put the shaded relief now with the river patterns, you can see there's dendritic down here, there's trellis up here, and then there's dendritic over here. And zooming in a little bit more, you can see how the rivers, they make these 90-degree turns. They're flowing across and then down the valley. And that's going to be one of the keys for this trellis drainage. Gorgeous. So dendritic, tree-like, it's the most common. Trellis drainage associated with folding. So tectonic compression, where convergent boundaries existed in the past. For example, the Appalachian Mountains, probably the best example of trellis drainage. Radial off a central peak. Parallel if the slopes are too steep for the river to just have the regular dendritic appearance. I'm just going to back up for a second and say that's what I was talking about with this. So you can see these slopes are steeper. These are flatter, more dendritic. Where they're steeper, the water flows down more than sideways as much. And so they tend to be more parallel, like this and this and this and this and this. Those are good examples of parallel. This is a really great example of dendritic. But even looking at the parallel, they look a little dendritic. So steep slopes, and if you've got a bunch of rivers that are flowing parallel to each other for this lab, it's going to be parallel. I'm not going to really nitpick and go, well, it's technically, no. They should be really obvious. And so let's go back to the examples again. Dendritic, trellis, parallel, rectangular, not that common. Faulting would create rectangular. Maybe the Wallace Creek area, if you remember back in Lab 12 when you were looking at the San Andreas Fault and the streams had been offset, that would be an example of rectangular. And then deranged drainage is one of my favorites. Those occur in areas that have been continentally glaciated. So everything gets scraped flat. As the glacier's flowing over the land's surface, everything is going to get scraped flat. And then when the glacier melts away, you've seen already now what recessional moraines look like and the till plain looks like underneath the glacier. So it's irregular. And unlike the Sacramento Valley, where there's a clear high ground up by Red Bluff and Redding, and then low ground in the Delta. So everything's flowing from high ground to low ground in areas of deranged drainage. There's like piles of loose rubble all over everything. So the rivers don't flow in all, yeah, this is good. All the rivers aren't flowing in the same direction at the same time. Like if you look at the Central Valley, everything is flowing towards the center of the Central Valley. All the rivers are flowing to the center of the Central Valley. Well, in areas with deranged drainage, that doesn't happen because everything is flat with random piles of loose debris. So here's from one of the textbooks showing dendritic, what it looks like, just as a diagram, and then on the surface, trellis, radial, parallel, rectangular, annular, and deranged. You don't need to know all of these. We're going to be looking at dendritic, trellis, radial, parallel, and deranged. Rectangular is really rare, and annular is also incredibly rare. They pretty much don't exist. Or there might be 2 or 3 on the whole planet. Not super common. So parallel, where the slopes are steeper. Dendritic, where they're less steep. And again, dendritic and trellis drainage. Trellis drainage is marked by a lot of right angles. Streams flowing in at a right angle. And we'll look at that later too. The folded Appalachian Mountains. So here we've got the Atlantic Ocean. Here we've got West Virginia. And in between, you had these folded mountains where you had a ridge and a valley and a ridge and a valley. And so the rivers sometimes flow across the ridges if the river had been flowing before that ridge existed. But otherwise, they're stuck in these valleys. And that's how you end up with that distinctive trellis Oh, that's even better. So you can see the rivers are flowing down the valleys, and then other rivers are coming in at a 90-degree angle. So that's going to be one of the big clues for trellis drainage. You're going to be looking for tributaries coming in at a 90-degree angle and folded parallel ridge lines for the trellis drainage. Radial, there's a central peak like a volcano, and then it's flowing away from that central peak. Parallel drainage is where it's steep, and so it doesn't, the river can't form the typical dendritic pattern, and more of the water is just flowing straight downhill. Another example of radial drainage, here we've got Mount Ruapihu, and how that would look on a topographic map, just looking at the streams. This is an example of deranged drainage. So I'm trying to think, like, as a student, what would I be looking for? A continentally glaciated location. So this is Michigan. A lot of the East Coast has been glaciated. So that's one clue. Just knowing where we're looking at, like I said, Michigan. Here's a diagram. Typically, you'll have streams that, like this one, it's flowing west and then north, and it's flowing into a lake, and now it's flowing east and now north. And yeah, so here we've got a river flowing along, and it's moving around these piles of debris. This is an esker. This thing, Blue Ridge right here, that's an esker. And I don't know if you'll be able to see it clearly in the video, but all of these symbols, these are the topographic symbol for swamp. So one of the other clues for deranged drainage is poorly drained. And by poorly drained, I mean there's a lot of swamps. If it was well drained, the water wouldn't be there because it drained out of there. So for deranged drainage, we're looking for an overall flat landscape, very flat landscape, and not an overall organized pattern to the rivers, like this one's flowing north and then west and then flowing east. Yeah, east, north, west. Yeah, around these random piles of debris. Skiff Lake, I think, is a kettle lake. And then some of these, like Prospect Hill, these are kames, those loose piles of debris left behind after the glacier melts away. And in fact, you can see the surface is, well, it's pretty flat here, but then there's piles, little mountainy piles of debris. So deranged drainage. One of the clues you'll look for is the river just kind of wandering aimlessly, and lots of swamps. So if it's wandering aimlessly and there's swamps, it's probably deranged drainage. The maps. What are the maps for this class? Well, here's one of the maps for the Sacramento River. You'll be using this topo map, and you'll also be using Google Earth. And in this case, the yellow line is the Glen Butte County line. And you can see that it doesn't match the river, the current river. For example, up here, Pine Creek, down here to Jenny Lynn Bend, up here to Indian Fishery. The dotted line or the dashed line, I suppose, with yellow, is the county boundary, and it represents where the river was when the counties were legally defined, which is why you should never, ever, ever use a river as any sort of political boundary, because they move. So that's some of the things we'll be looking at. Up here is Dunning Slough. Down here is Ord Ferry. It's just a road. You'll be calculating what the relief is between them using Google Earth, and then figuring out what the length is between them using the map. And then you'll figure out the sinuosity and some other stuff. Close-up of the boundary and how it just doesn't match. So these people are legally in Butte County, but they're on the Glenn County side of the river because the river moved and the boundary didn't. What else was I going to say? Yeah, the semicircular, these circular things, there's a lot of circles. Lots and lots, like here, Phelan Island, Murphy Slough, and Golden State Island. There's another these are all meander scars. This is a meander scar. That's a meander scar. Dunning Slough, I'm not sure what that water is. I think it's artificial, but that's another meander scar. So initially, the river was flowing through it as just part of the channel, and then it became an oxbow lake. Like Murphy Slough down here looks like a good example of an oxbow lake because there's still water in it, and then eventually it dries out and you'll end up with a meander scar. Some other examples, yeah. Yeah, that would be a meander scar. Murphy Slough would be an oxbow lake in a meander scar, or at least as it appears here on the map. And some of the things I'll have you do is like, well, compare the way it looks on the map with the way it looks in Google Earth presently. So comparing the older map with more current reality is part of what you'll be doing. The contour interval for the map is given, the scale for the map is given. So if I tell you how many inches I measured, it's this many inches from whatever Dunning Slough to Ord Ferry Road. If you know the scale, you can figure out how many feet that is on the ground. This says 14.1. That's a typo. It'll actually say yours will say figure 15.1. This is a map that I made over aerial imagery showing all of the past river channels of the Sacramento River from 1896 with the oldest channel up to the newest channel in the dark red, the 2012 channel. And you can see how the river has changed shape over time. Like it used to flow through there, and before that it was flowing through there, and now it's flowing over here. So some of the questions I'm going to ask you are, when was the last time there was water flowing in a given part of the river that is now dry? So you'll have to just look it up and figure out what the color is for that section of the river and then what date that applies to. And this is a map that I made using a digital elevation model. Often with a DEM, you can see things that you can't see on a regular topographic map or on aerial imagery. Some of these features I'm asking you about, what are they? What are these features that you can see on the DEM that maybe you can't see on the topo map? So let's go through Lab 15 and see what it is that you're supposed to do. Okay, so here's the start page for rivers. Here's the Fisk diagram, one of the Fisk diagrams. I included a link. The site Radical Cartography had a really cool article on the project. I included a link to the glossary and some of the key terms that you need to know. This lab has a pre-lab quiz, a discussion topic, and a lab activity. Next up, a whole bunch of videos, super quick intro, this video, a video on meanders by Zentner. Love that guy. Another video on meanders. I would really highly recommend watching them. I think I'll also include my lecture video if you haven't. Like I said, if it's been a while since you've had the chapter on rivers or your teacher hasn't covered it yet this semester, I'll include my lecture video. Here's the information. This page has, I hope, everything you'd need to know if you haven't had the rivers chapter already. So some definitions, diagram of drainage patterns, here's the floodplain diagram with like Oxbow Lake and meander scar and what they mean. Here's some more discussion of meandering and how that works. There's that video. I think I made this into a GIF, but here's a video version talking about folded landscapes. So a lot of information. I highly recommend paying attention to the meandering and the key terms for floodplain features. As usual, you've got a pre-lab quiz, we've got a discussion post, and the rivers activity. So let's take a look at this. So for this lab, here's a link to the maps that you need for the lab, and here's the scale, elevation, distance, and slope sheet from Lab 13. And I also made a quick handout to try to help you identify some of the features that you'll see. So you're doing the stuff with drainage patterns, you're doing some stuff with maps on the Sacramento River, you're finding relief, you're finding distance, you're finding slope, you're finding sinuosity, identifying when water was flowing down a certain part of the river, identifying some floodplain features. We're also going to be looking at the Mississippi River and figuring out the scale of the map. We're going to be figuring out relief. We're going to be figuring out sinuosity and the slope of the river. We're going to be looking at, sorry, I didn't want to go too fast, at floodplain features. We're also looking at the American River with some of those same features, floodplain features, slope, and sinuosity. So that's it for Lab 15. I wish you good luck. If you have any questions at all, please come to Zoom so that I can answer them and you can succeed at your lab.